Right, this is Physics 202, Chapter 1 homework. This first problem we're going to skip, and I might come back and add something later, but we're going to skip this for now. So let's just go down to problem number 2. On problem number 2, it says 3 charges are arranged as shown in this figure. Find the magnitude and direction of the electrostatic force on Q1. So first, just let's just sketch in the forces that are at play on Q1. The force on Q1 due to Q3 have a positive for Q1 and a negative for Q3, so opposite charges attract. So the force on particle 1 due to particle 3, I'll call that F13, is in that direction. And then the force on particle 1 due to particle 2 is in this direction. I'll call that F12, the force on particle 1 due to particle 2. Now we also need to find out what are some angles and distances here. First of all, I want to know what is this distance. Let's see, I have a triangle here. So I can find this distance is the square root of 2 squared plus 5 squared. And that is equal to, well, the square root of 4 plus 25, the square root of 29, which is 5.4 meters. So that distance is 5.4 meters. I'm also going to need to know some angles. Let's figure out what this angle is. I'll call this angle phi, and phi is going to equal the inverse tan of opposite over adjacent. That's the inverse tan of 5 over 2, and that's equal to 68 degrees. In particular, though, I want to know if I draw my x-axis here, I draw on my axes. Here's my x-axis, my y-axis. I want to know what is this angle, and since this is equal to 68, this will be equal to 90 minus 68, which is 22 degrees. All right, so now I can draw my forces on an xy coordinate grid. I have F13 at 22 degrees from the x-axis, and then F12, which is in the negative y direction. All right. Now let's go ahead and find the magnitudes of F13 and F12. F13 from Coulomb's law is equal to K Q1 Q3 over the distance squared. So that's 9 times 10 to the 9th. Let's see, that is Newton meters squared per Coulomb squared times Q1, which is 6 nanocoulombs. That's 6 times 10 to the minus 9 coulombs times 3 times 10 to the minus 9 coulombs. Notice that I don't use the signs for the charges. The signs tell me the direction of the force, but I've already accounted for the direction of the force by saying that opposite charges attract, like charges repel. And then over the distance squared, that's 5.4 meters squared. And I find that F13 is 5.6 times 10 to the minus 9. And then I want to know what F12 is. F12 is K Q1 Q2 over R squared. It's going to be 9 times 10 to the 9th times 6 times 10 to the minus 9. Remember, nanocoulombs, you'll need to know those small metric prefixes, nano, micro, maybe pico later. Q2, what was Q2? 4 nanocoulombs. Good way to remember nano is nano looks a lot like 9. And you know it's small. Over the distance squared, it's 2 meters. If you do that, you get 5.4 times 10 to the minus 8 newtons. All right, so now if I notice that the force F12 is a lot smaller than the, is a lot bigger than the force F13. Now I want to find the x and y components of each of these forces. I'll make a little table like we did last semester. These are going to be my x components. These are going to be my y components. The x components of F13, that's going to be F13 cosine of 22. And then this is going to be F13 sine of 22 for the x and the y components. F13 cosine of 22 is, let's see, 5.6 10 to the minus 9 times 22 cosine. I get 5.2 times 10 to the minus 9. And then F13 sine of 22 is 2.1 times 10 to the minus 9. And then I find my x and y components for F12. The x component was 0. The y component is negative 5.4 times 10 to the minus 8. Now when I add these numbers up, I get 5.2 times 10 to the minus 9 newtons. That's my x component. It's in the positive x direction. And then in my y, I get negative 5.2 times 10 to the minus 8. So now if I were to sketch out my force vectors, these are x and y components. I have my x component, which is in this direction. That's 5.2 times 10 to the minus 9. And then my y component, excuse me, I made a mistake here. Let me fix this. This shouldn't be 9, it should be 8. My y component is negative 5.2 times 10 to the minus 8. Notice that it is 10 times bigger. So I'm going to draw it to scale. It's going to look like that. And then the resultant vector will start here and then go down there. So I want to know the magnitude and direction. I want to know that angle theta. I want to know the magnitude. Well, the magnitude of that force from the Pythagorean theorem is going to be 5.2 times 10 to the minus 9 squared plus 5.2 times 10 to the minus 8 squared. I left the negative off because it's squared. And since the y component is so much bigger than the x component by a factor of 10, my magnitude is dominated by that y component. So the magnitude is the same as the magnitude of the y component with rounding. So that's my magnitude. And now to find the angle theta, it's going to be the inverse tangent of the y component over the x component. That's opposite over adjacent. That is the inverse tangent of 5.2 times 10 to the minus 8. Divided by 5.2 times 10 to the minus 9. So that's the inverse tangent of 10, which is 84 degrees. And it's below the plus x-axis. All right, a basic vector problem, and we've done these before, but it's just adding in the complication of you have to use Coulomb's law here, which describes the force between two charged particles in order to find the magnitude of the force. But basically, it's the same problem as we've done before with vectors. All right, an object with a net charge of 12 microcoulombs is placed in a uniform electric field of 610 newtons per coulomb directed vertically as shown in this figure. What is the mass of the object if it floats in the electric field? All right, so in order for this object to float, it has two forces acting on it. The first is the weight of the object, and then the second is the force due to the electric field. In order for this to float, the electric force has to equal the weight force. The electric force is given by Q times the electric field, and it's equal to M times G. All right, so I'm just looking for magnitudes here. I want to know the mass. The mass is equal to Q E over G. That's 12 microcoulombs. The electric field is 610 newtons per coulomb. Notice that my units leave newtons in the numerator, divided by 9.8. And then that'll give me a mass. My mass is 7.5 times 10 to the minus 4 kilograms. I also want to know what is the direction, or what is the charge of this. Is it positive or negative? Remember, a positive charge feels a force in the direction of the electric field. So if I have a field line in this direction and I have a positive charge here, then my force is also in that direction. Here, I have an electric force that is in this direction, and an electric field that is also in that direction. So that means that it has to be a positive charge. Q must be positive in order for the force to be upward. If it were negative, the electric force would be down and it wouldn't float because the electric force and the gravitational force would be in the same direction. However, if my electric field was drawn like this and I wanted it to float, I would have to have a negative charge, and then the electric force would oppose the electric field. The weight would be the same direction. Proton is accelerated by a constant electric field of magnitude 1250 newtons per coulomb. I want to find the acceleration of the electron. And what is the electron speed after a certain amount of time? T equals 1. Assuming it starts from rest, that means that V naught equals 0. And I want to know what is its speed. All right, here, I'm looking at magnitudes here, so I'm going to put some bars around those. All right, so I first need to find the acceleration. I know from Newton's second law, F equals ma. All right, so my acceleration is equal to F over m. In this case, the force that I have applied here is an electric force. I know that F is equal to QE. That is the force due to an electric field, is the charge times the magnitude of that electric field. A proton is 1.6 times 10 to the minus 19 coulombs, and the electric field is 1250 newtons per coulomb, divided by the mass. The mass of a proton is 1.67 10 to the minus 27 kilograms. You'll be given all these things: mass of the proton, mass of an electron, charge of a proton and electron, the fundamental unit of charge. But they're also just good numbers to have because you use them a lot. And if I put that in, I get 1.2 times 10 to the 11th. That's a whopping big acceleration. All right, so that was for part A. But these are big forces that are applied, and also very small masses. So, or rather, very small masses, and so the forces cause a very large acceleration. So now I need to know the final velocity. I need to remember back our kinematics. V equals V naught plus AT. It's equal to 0 plus the acceleration. And then the time is 1 times 10 to the minus 8 seconds. And so for part B, that gives me 1,200 meters per second. Sort of time of flight calculations are very important when you're dealing with these types of things, where you're manipulating the paths of charged particles. Like, for example, in a mass spectrometer, we'll see it. Well, here we go. Number 5, a beam of electrons must travel between two charged plates and exit so they just miss the top plate. Electrons are traveling at that speed, 1 times 10 to the 4th meters per second. What must be the magnitude and direction of the electric field for this to occur? All right, so I want these beam of electrons. These are negatively charged particles, electrons. I want them to travel through this plate. They go along here and they have no force, so they just move in a straight line. But as soon as they come into this electric field, I want them to feel a force that will bring them upward and cause them to move so that they just exit at that point. That means that I want them to travel this amount of distance. That distance, by the way, is 0.1 over 2. It's 0.05 meters. All right, so my y distance that they're going to cover is 0.1 divided by 2. It's 0.05 meters. And the time that they're going to cover it in, I also want to know. Now I know their velocity in the x direction. That's vx. It's equal to their initial velocity. And then this is the distance that they travel. And so I can say that t is equal to vx, excuse me, not vx, L over vx. All right, that's going to be 0.5 meters over 1 times 10 to the 4th meters per second. This is sort of like the projectile motion problems that we worked last semester, where you had it accelerating in the y direction, but it wasn't accelerating in the x direction. And so we can, if we know the distance and the initial velocity, we can find the time in this way. And I get 5 times 10 to the minus 5 seconds, 50 microseconds. All right, so that's the amount of time that the particle takes to get from here to here. That's also the amount of time that I want it to get from here to here. So now I need to find the acceleration in the y direction. I'm going to do that over here. I know that y is equal to v naught y plus 1/2 ay t squared. I was told that it starts at rest in the y direction. I wasn't told that explicitly, but it's moving purely in the x direction. So when it gets to this point, it has no y velocity. All right, that means that v naught y equals 0. My y displacement is going to be 0.05 meters, and that's going to equal 1/2 ay times the time, which is 5 times 10 to the minus 5 seconds. We'll square that and solve for ay. I find that ay is equal to 4 times 10 to the 7th. So that's how fast it must accelerate when it's going from here to here in the y direction, so that it covers this amount of distance, 4 times 10 to the 7th meters per second squared. Now we want to know what is the electric field that will cause that. All right, so I know that from Newton's law that F equals ma. And then based on our definition of the electric field, F is also equal to QE. All right, the force due to an electric field. So I can set these two equal. I can say that ma equals QE. I'm going to solve for E. It's equal to ma over Q. Okay, I know what the acceleration is. That's my acceleration in the y direction. And so now I can solve for these things. Mass is the mass of an electron. That's 9.11 times 10 to the minus 31 kilograms. Again, just a number that's good to have sort of on the tip of your tongue. 4 times 10 to the 7th meters per second squared divided by Q, which is 1.6 times 10 to the minus 19. I'm going to leave that as positive, even though it's an electron, because we're going to come back and address the whole direction thing. All right, so that gives us an electric field of 2.3 times 10 to the minus 4 newtons per Coulomb. Okay, now I want to know, is this going to be up or down? I have an electron that's traveling through these two charged plates. I want the force on that electron to be up. That means that the electric field has to be down, because an electron feels a force opposite the direction of the electric field. All right, so the direction of this is going to be down in the negative y direction. So I could also write it as negative 2.3 times 10 to the minus 4 newtons per coulomb in the j direction. Either way you want to write that is fine. They're both correct. All right, this figure shows the electric field lines for 2-point charges. Determine the ratio of Q1 to Q2. And what are the signs of Q1 and Q2? Let's do part B first. Electric field lines originate from positive particles and end at negative particles. All right, so I already know then that Q1 over Q2 is going to be a negative number. Because Q1 is positive, Q2 is negative. Now, if I want to know the relative strengths of the charges, or the relative sizes of the charges, I count the electric field lines. Because the electric field is directly proportional to the charge. All right, the electric field is directly proportional to the charge. Remember, E is KQ over R squared. So I have 1, 2, 3, 4, 5, 6, 7, 8 field lines over here. Just 4 field lines over here. So my my ratio of charges Q1 over Q2 is going to be negative 8 divided by 4. 8 field lines over here, 4 over here. So that means that Q1 is twice as big as Q2, and the two are opposites. Q1 over Q2 equals negative 2. All right, I want to find the expression for the electric field at the point P in terms of Q, D, and Z. This is a dipole, very important in a lot of chemical simulations. I know that at point P there are 2 components to the electric field. The electric field at point P is equal to the electric field due to the positive charge minus the electric field due to the negative charge. See, I imagine putting a positive particle here, and I ask myself, what is the direction of the force on that particle? And then that's the direction of the electric field. So if I put a positive particle here, the force due to that charge would be in that direction. So that's going to be the direction of E plus. And the force due to this charge will be in that direction. So that's going to be E minus. And notice that I drew E negative a little bit smaller because this charge is further away from point P. All right, so I can further say, since my electric field is defined as KQ over R squared, that E plus is KQ over R plus squared minus KQ over R minus squared. All right, so that's just, I'm just saying this distance is R plus and this distance is R minus, but now I'm going to express this in terms of Z and D because I want this to be all in terms of Q, D, and Z. So I have KQ for Z minus 1/2 D squared minus KQ over Z plus 1/2 D squared. All right. It might not seem obvious to you why we would do this, but once we get to the end, you'll see that we get a really nice expression for the electric field that's only in terms of Q, D, and Z. So let's see, I left a D out here, so that should be D. Now, what we're going to do is we're going to factor out 1 over Z squared from the denominator. Just to simplify it a little bit. And so, for example, if I did that, I'm going to sort of write this as a little cloud. If I do that, so 1 over Z minus 1/2 D squared becomes 1 over Z squared 1 plus D over 2Z. bigger. Z squared times 1 plus D over 2Z squared. So I can rewrite this. And when I factor out that 1 over Z squared, come down here, do that, and I can rewrite this as E is equal to KQ over Z squared. There's that 1 over Z squared that I factored out. Times 1 minus D over 2Z to the negative 1. That's from minus 1 plus D over 2Z. Excuse me. That's also to the negative 1. Let's see. It looks like I have a mistake up here. I'm sorry. Let me come back up here. This should be a negative right here. It should be 1 minus. All right, D over 2Z squared. All right. So now, as I said, that might not be obvious to you why we would do that, but we can make this substitution using the binomial theorem that when Z is much, much greater than D, when Z is, that is, you're much farther away than the two particles are close together, you can use the binomial theorem, which says that 1 plus x to the n is equal to 1 plus nx over 1 factorial plus n minus 1 x cubed over 2 factorial plus dot 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 dot. And that goes on forever. So we can make that substitution, but we're just going to use these first two terms, and we're going to let x equal d over 2z. All right, so this is my x, my 1 plus x to the n. And so n is going to be minus 1. So we can use those, we can substitute that in. And I get this. I get E is equal to KQ over Z squared times 1 minus negative 2 D over 2Z minus 1 plus negative 2 D over 2Z. If I simplify that again, I get KQ over Z squared, 2D over Z, and then simplify it, just combine those Z's, I get KQD over Z cubed. Let's see, I think I left a 2 in here somewhere that I shouldn't have. Let's see, that goes 1 minus 1. Those 2's cancel out. Yeah, I guess there's a 2 in here. I'll have to come back and check that. I'm not certain that there's supposed to be a 2 there. So I'll come back and check on it. If it's a mistake, I'll come back and fix it. All right, I'm going to find the electric field at point P. So the dipole is sort of a special case, but it's a very important special case because the dipoles occur a lot in nature. We also can sometimes get charges in regularly shaped objects, like for example a charged ring, and that's what we're going to do here, or a charged disk, which we'll do in just a minute. So I want you to find the electric field at point P and then express it in terms of Q, Z, and R, where Q is the total charge on the ring. First we want to consider a charge element, and that is going to be, we'll call it dq. It's the charge on this little section of the ring. And that charge is going to equal to lambda, which is the charge per unit length, times ds, which is the length of this little segment, ds. Then I can find the electric field just due to that little section is going to be k dq, k times the charge on that little segment all over r squared. And since dq is lambda ds, I can write it like that. Now, I can also say that r, which is this, by the Pythagorean theorem, is equal to the square root of z squared plus r squared. Remember, I want everything in terms of q, z, and r. So I can say then that dE is equal to k lambda ds all over z squared plus r squared. All right. Now I can show that the total electric field in the y direction, or that the total electric field is in the y direction, and that the x components cancel out. Imagine that I have an electric field in this direction due to this section of charge, and then due to this section of charge, my electric field is in that direction. All right, now these have equal but opposite x components, but the y components add up. So the y components are in this direction, but the x components are in that direction, so they cancel out. So I only have the y components. I'm going to call this dE perpendicular because it's perpendicular to the ring, or you could call it dEy if you want. And that's going to be dE cosine of the angle theta. That's this angle theta. Notice it's cosine because that angle theta is measured off the x-axis, or excuse me, off the y-axis and not off the x-axis as it usually is. All right. So dE is k lambda ds over z squared plus r squared. That's just from up here. And now I have this new term, this cosine theta. Cosine theta, remember, is adjacent over hypotenuse. This is my adjacent side. This is my hypotenuse. So it's going to be z over z squared plus r squared to the 1/2. So now I can keep going. My dE perpendicular, which I'm just going to go and call it dE now because that's going to be my total electric field. It's going to be k lambda z ds over z squared plus r squared to the 3/2. I think we're about ready to integrate now because you see z, as we go around this, z doesn't change. Big R doesn't change. K, of course, doesn't change. Lambda doesn't change. So I can take all that out. I'm going to integrate. The integral of dE is just going to be the electric field. It's going to be k lambda z, or z squared plus r squared to the 3/2, the integral of ds. And now we want to determine our limits of integration. ds is an arc on that circle, and we want to integrate over the total circle. So it's going to go from 0 to 2 pi r. So my electric field is going to be k lambda z 2 pi r. Excuse me, this should be a big R because it's the radius of my circle, divided by z squared plus r squared, the 3 halves. And then if you say, you can do this, let's come back up and I'll do this over here. Q is equal to lambda times the circumference of the circle, based on just the definition of lambda. And so I can simplify this a little bit more. I get kqz over z squared plus r squared 3 halves, and that's the magnitude of the electric field. Notice that if z is much, much bigger than r, then this simplifies, the r term becomes insignificant, and this simplifies to just kq over z squared. So if I'm really high above this ring of charge, it's going to look like a point charge, is what that's saying, because that's the same expression for the electric field due to a point charge. All right. It's really the method in these that's important in how you integrate over these regularly shaped objects, because this comes up a lot in physical scenarios where we want to integrate over some function over a regularly shaped object such as this. Okay. This is a charged disk. I want to find the electric field due to this charged disk. I'm going to start with a charged ring, because I know that for a charged ring, the electric field is kzq over z squared plus r squared to the 3 halves. So I'm going to imagine my differential element now. Instead of being some little piece, I want to make it a ring of charge. Right? Because I know the electric field at this point due to a ring of charge. Right? Now I'm going to call this distance little r, and from this I'm going to let big R become little r, because now I want to express the electric field due to this ring of charge, and I'm going to let little q become dq. All right, so now my electric field due to that differential element is going to be kz dq over z squared plus r squared to the 3 halves. All right, so I can also define this charge on this differential element. I'm going to let dq equal sigma, which is the area density, times 2 pi r, which is their circumference, times the width, dr. So sigma is measured in coulombs per square meter. It tells me how much charge per area. This is the circumference. This is the width. Those combined give me the area, and that gives me the charge on that differential element. Then my dE becomes this. My differential element of the electric field is kz sigma 2 pi r dr divided by that z squared plus r squared to the 3 halves. Now I'm ready to integrate over all these things. So my electric field, that's the integral of dE, is going to be kz sigma pi times the integral of z squared plus r squared to the negative 3 halves times 2r dr. I'll show you why I wrote it this way. You don't know necessarily why you should write it this way, but let me show you why. Because I'm going to use substitution. I'm going to let x equal z squared plus r squared. And then I'm going to let m equal negative 3 halves. And then dx, which is the derivative of x, is going to be 2r dr. That is dx dr is going to be 2r, so dx is 2r dr. So, okay. So, in these little substitutions, and then I can say that the electric field is kz sigma pi times the integral of x to the m dx. Using those substitutions that I've made, so this is going to be kz sigma pi times x to the m plus 1 over m plus 1. Now if I make those substitutions back in, I get E is equal to kz sigma pi z squared plus r squared to the 1/2, excuse me, to the negative 1/2, divided by negative 1/2. Skipping a few steps here, but if you look carefully how I make these substitutions, I'm just substituting these things back in for x and m. And then I'm going to integrate this over my limits of integration, which are r equals 0 and to r equal r, because I'm going from here all the way out to here. So I want to integrate over those limits. Okay, so I apply the limits. I'm going to rearrange a little bit almost to the end now. I have a negative let me go back here for just a second. I'm going to factor out that negative 1/2, so I have negative 2. And then I'm also going to distribute that z throughout. So I get negative 2 k sigma pi. So I'm doing two things. I'm removing that negative 1/2 from the denominator, and now I'm taking this z and I'm multiplying it to both sides, distributing it. So I get z over z squared plus r squared to the 1/2 minus 1. This is my final answer. That's the answer. Now, notice that if r goes to infinity, or it gets really, really big, this would be like an infinite sheet of charge. Then E is just going to be 2k sigma pi. So that's the limit for that. E is 2k sigma pi. All right, that's the end for chapter 1. You can be responsible for one of those derivations. We'll talk more about it in class.